department, and today I'll be talking about preconditioning a conjugate gradient method for deep generative learning models. So just to start, I want to give some applications, just a little motivation. Earlier, this tied in really well. We talked about imprinting a little bit. So that's one of the example applications that deep generative learning models can do. Basically, it's taking distorted images and we're kind of filling it in with a deep fake in a sense. As well as we also talked about GANs, which, believe it or not, was the second one that I was going to talk about. An application that people do is in drug databases. A lot of times we want to identify different isomers that we can rotate around the chemical compounds in order to detect new drugs. And it can take a lot of time and a lot of effort. So being able to do this utilizing a GANs network on top of the generative learning speeds up the process. So what is a generative learning model? So generative learning models take some type of distribution, in this case a unit Gaussian. We apply the model, which is usually some type of neural network, and we're going to generate a new distribution. So you can think of this by like taking a ball of slime and you're kind of stretching it out. You're creating a new distribution, a new shape there. And how we generally model it is using a normalizing flow first, because we have to put it into math before we can put it into the neural network. So what normalizing flows are, they're invertible mappings between data distributions, so the old one to the new one that we want. And we typically like to design them to be easily computable for the normalizing flow if we need to calculate the inverse and if we need to calculate the Jacobian, which is all the different first and second derivatives that we need. And we want to make it expressive, which basically means we want our generated distribution to match what we want our true distribution at the end to be. So in terms of now taking that and putting it into a neural network, in this case, I'm utilizing an input convex neural network. And we're going to kind of just for the brevity of this talk, not go too much into this, but essentially what this network does, the architecture takes an input, y in this case, and like a feed-forward network, we have weights and biases, activation functions are passing through some layers. However, the unique thing with input convex neural networks, first is that we're utilizing convex activation functions here, and secondly is that we are applying an activation function directly related to the input every time. And the main purpose of utilizing this input is going to come in the training, because what this neural network is going to do, it's going to optimize the distance we need the points in the distribution to travel to make the new distribution. So we want those inputs to travel the least distance possible. So we need to keep track of them. So now putting that all together, how we connect the ICNN to the normalizing flow to generative learning models. We basically are going to let this capital F represent our ICNN. We're going to let theta be collections of those weights and biases that we're going to train using the neural network. And there's this known relationship that was produced by Amushu and Holter that says that our normalizing flow, F, is going to be equivalent to gradient approximations of all the different computations we have to do inside an ICNN. Which means we're going to have to compute Hessians in this case, which is going to be very, very costly. So overall, this is kind of the architecture of the neural network. So we have a forward pass where we're estimating log determinant of the Hessian. We'll talk about that in just a second. We're checking, okay, how close are we to our distribution? We're going to estimate the derivatives, do backward propagation, update those weights, find the weights and biases that we want, and then repeat the cycle over and over again until we get an approximate solution to what we want our distribution to look like. So log determinant the Hessian, the thing that we want to try to minimize for a neural network in our optimization problem here, that basically is going to be how we measure the distance between the input where we started to where we're going. We want to try to minimize that distance like I talked about. So that's a measurement of how we do that. However, we encounter some problems in actually training this network because the Hessian is computationally expensive. We have to compute many, many derivatives. Think about if we have a system that has like 50 variables, then we have to be able to take all the derivatives of those variables with respect to each other, all the different inputs. It can get very computationally expensive. And on top of that, we have to do the derivative as well of that Hessian. So it's unstable. So a solution that was projected by Huang et al. From 2021 is they used what's called a stochastic Lantrose quadrature trace estimator to estimate this value. And then for the derivative, we used this is what's known as the Hutchinson trace estimators. Now, the Hutchinson trace estimator does have an issue because of an inverse Hessian, which again, as I mentioned earlier, we don't really want to compute the inverse of anything. It's a little too hard. So we estimate that using what's known as a conjugate gradient method to solve this V star is replacing this V transpose H inverse inside our estimation for the trace. And the reason why we pick conjugate gradient specifically is because it's what's known as a Krylov subspace method, and it's supposed to converge in n iterations. So if you have, if you're in n dimension space and variables, say it's like 50, you should converge theoretically in at most 50 iterations then. So here I have a little model, which we'll see. It's okay. Video unfortunately isn't going to play, but basically what happens is this is the input we gave it, which is an input. And this is an experiment done by Huang et al. That I've reproduced here. You have the unit Gaussian here, and we made it into 8 small Gaussians, kind of in this ring formation. So what the video would show is kind of all those different points traveling out to create this 8 Gaussian. That's what we're trying to do. So this is what they had. Now, problem with that is that it takes a long time. So we thought that we could speed up the process using what's known as a preconditioner. So convergence of CG is going to depend on the condition number kappa. And if kappa is big, it's going to take a lot of iterations. However, if we can make kappa smaller, we're going to get faster convergence with the CG. So we want to find a way to reduce the condition number. We do that using preconditioning matrices. In this case, we're going to call it M. And we want M to be easily invertible because it's going to add extra computation. And we want it to make the eigenvalue distribution smaller, where eigenvalues are these lambdas. So by making it smaller, we make the maximum eigenvalue closer to the minimum eigenvalue, which theoretically should make kappa smaller in this case, and therefore reduce the overall iterations that are required. So the preconditioner construction here, we used what's known as a projection subspace method to produce this matrix M here. And essentially what our M is doing is, in this prototypical example, we have the eigenvalues in this case, since it's a diagonal matrix, all the eigenvalues are on the diagonal. So 1,000, 2, 35, 3, 54. And we want to shrink that distribution. So our preconditioner, what it does is we set a threshold for it. And anything that is greater than that threshold is we are just going to shrink right down to 1. So as you can see here, the 1,000, we shrink right to 1. But the 2 didn't meet our threshold, so we keep the 2. However, thinking about the calculations of this, maximum eigenvalue here was 1,000 to 2. So that'd be a condition number of 500. Now maximum is 5 to 1 is our lowest. So condition number of 5. So we have a much smaller condition number. And this translated into our results. So in terms of, this is just a 2x2 matrix system. So should take 2 iterations as n iterations for CG. We see that the preconditioner actually doesn't do better than CG. Now, reason for that is because, like we said, we added computational cost. So this means that per iteration, the iterations are going to take more. Where we see the value in preconditioning CG is going to be when we have these larger systems. Here on this graph, we have a graph where the matrix dimension is on the bottom, and we have the number of iterations on our y-axis. So we have 50 going to 4,000. So this is a 50 by 50 matrix going to 4,000 by 4,000. And what we see is that for the preconditioning CG now, with these larger systems, we're staying around 20 iterations. However, beforehand, with the control CG that previously existed, was around 140. So we basically shrunk down the number of iterations by about 1/7 here. So significantly more. Now, each iteration will have slightly more computational time, but as we see here, it's only about double, is about what it is. So really, this would rank around this amount of computation. So it's about 1/4 of the computation that we used to require, and therefore is much faster. So in terms of the expressiveness, because we also want to make sure that these are giving us the same results. Here we have the unit Gaussian again. So this was Huang et al.'s example. And here we have a preconditioned 8 Gaussian that we did. And looks about the same in this case. There are some slight differences because, again, we're using estimations and some stochastics in this, but it gives us equivalently the same expressiveness that we want. And we also tested it on a Swiss roll example here too, which gave us similar results as well, the expressiveness. So what to take away from this? Basically, we see that higher computational expense of a Hessian, as well as higher storage requirements, motivates us to search for approximation methods, such as CG in this case. And preconditioners, such as M, is going to reduce the number of iterations for these higher dimensional systems, but for lower dimensional systems, it's still okay just to use CG. And in this case, we get the same expressiveness and some possible future explorations with this. There's what's known as a Hutchinson ++ trace estimator, which theoretically should speed up this estimation even faster, as well as other preconditioner constructions that are out there. There's always better preconditioners that we can find here. And in addition to this, I also do some work on neural networks, and also I have just gotten into doing some Navier-Stokes work as well. I want to have a few acknowledgements here. I want to thank my collaborators who worked with me on this project, Lauren Proctor, Edward Schau, and Stephen Stern. I want to thank Florida University and FSU Libraries for having me here today. I want to thank the people who funded and gave us the resources for this, which was the NSF and then the Emory University Department of Mathematics. The advisor on the project, which was Dr. Ren Jie, and 2 postdocs who helped with the project as well, Dr. Huan He and Dr. Yuling Shi. All right, here are all my references, and thank you so much.